Hey, welcome out to our next talk entitled "Toward Machine Intelligence Capable of Nobel Caliber Science," to be delivered by Alexander Lavin. Just before we start, I just want to let everyone know that you can also visit our booth to take advantage of the offers we have for participants today for the conference, and then also take advantage of job opportunities that are posted on our app. So just a little introduction before we start about Alexander. Alexander is a world-leading AI researcher and software engineer. He's specializing in probabilistic machine learning, scientific computing, and human-centric AI systems. He is the founder and chief technologist of the Institute for Simulation+Intelligence, which is a public benefit-focused research organization aiming to reshape the scientific method for the machine age, building novel technologies to synergize AI and simulation in areas such as climate, symbio, nuclear energy, and more. For the next hour, Alexander is going to have attention delivering the talk. If you have any questions, just type it in the chat. Then at the end of the talk, we'll relate that to Alexander during the Q&A section. So Alexander, you can start the talk now.
All right, thank you so much for that nice intro. And everyone, thank you for joining. Welcome. I'm glad you are tuning into my talk. As you mentioned, I'm Alexander Lavin, founder and chief technologist of Pasteur Labs and the Institute for Simulation Intelligence, which are sister
Alexander,
corporations.
you can start the talk now, okay?
Do you not hear me?
We can hear you. Go ahead, please.
Okay, yeah, I'll keep going. Yes, so as I was saying, I'd like to share with you some of the machine intelligence technologies that we're building, essentially to shift perspective and reinvent or flip workflows to think differently about the questions to ask in science and intelligence, and how to approach them in areas like climate science and energy systems to material science and particle physics. Let's begin with some signs of science with a brief look at how we view the state of scientific progress. You might have heard renowned economist Tyler Cowen saying that scientific progress is slowing down, which is supported by a wide variety of metrics across fields and over the past several decades, and similar sentiments from other economists in other fields as well. And philosopher of science Ian Hacking says that normal science does not aim at novelty, but actually at clearing up the status quo. It tends to discover what it expects to discover. And I'm sure many in this audience are nodding along in agreement, whether thinking about the state of scientific publishing or big tech innovations or big pharmacos and so on. And one can point to many, many reasons for this slow of scientific progress, for example, institutional structures. But in this talk, I would like to dive into computational bottlenecks that are holding back science and intelligence. And on the horizontal axis, you might notice this term paradigm shift that I used intentionally. It was the physicist Thomas Kuhn who first introduced this phrase back in the 60s. And his thoughts really altered the way that many of us look at the philosophy behind science, where standard accounts of science project steady cumulative progress. Kuhn saw discontinuities, sets of alternating normal and revolutionary phases. And Kuhn, this version suggested that the last thing that normal scientists seek to do is to refute theories that are embedded in their paradigm. It's actually the normal way of doing science. It incentivizes scientists to not try to refute anything supporting their paradigm. And the paradigm shifting opportunity here that I'd like to talk about, and is the basis for the companies that I've started, is at the intersection of simulation and artificial intelligence, where these technologies can be combined in synergistic ways, not necessarily to use simulations like video game engines to train reinforcement learning agents that you've seen at places like OpenAI and DeepMind. This is an area that we're calling simulation intelligence. Technologies, and in a way that capitalizes on this paradigm shifting opportunity to define new scientific methods. As I alluded, I started this as a focused research organization with folks from Schmidt Futures, Eric Schmidt's venture lab here in New York City. Most of what I talk about is with Pasteur Labs, which is the for-profit public benefit arm of this FRO. The sister organization is a nonprofit Institute for Simulation Intelligence, which supports PhD students and postdoc appointments. With these two, I lead a small team of amazing scientists and engineers from places like DeepMind, Cerebras, GraphCore, CERN, NASA, Intel, and more. And we work across organizations from government such as NASA and DARPA to industry like NVIDIA and Microsoft, and partner with tons of world-leading academic labs. And we're building platforms for better integrating simulation and AI. Some of our novelties are in fundamental research like causal discovery. Others are towards applications like energy storage. Science, then AlphaFold. The recent landmark results from DeepMind's AlphaFold in a CASP competition for protein structure prediction really showed dominance over the field for state-of-art in three-dimensional protein structure modeling. Overall, there were several deep learning innovations to assemble the network that is purpose-built for protein structure. And this approach to computational protein structure prediction is the first to achieve near experimental accuracy in a majority of cases. And while the success of AlphaFold is undeniable, there are questions that remain as to how much the AlphaFold modeling framework and knowledge about it can be adapted to solve other similar fundamental challenges in molecular biology, such as RNA folding, chromatin packing. Basically, we want to ask how much effort would be needed to customize the tool to other areas to make a fresh contribution to them, and how to evaluate the contribution of the AI tool itself versus the human in the loop at most stages. And this also leads to a more philosophical outcome of AlphaFold. That is, this implication that a scientific challenge can be considered partially or totally solved, even if human scientists are relatively unable to understand or gain any knowledge from the solution, thus leaving open the question of whether the problem has really been solved. And AlphaFold, like I said, is clearly impressive, and it does fall under the umbrella of methods in this subfield that we're calling simulation intelligence. Although for my group specifically, we focus on methods that are quite a bit different, and I'll get into that later. SI describes a field that merges scientific computing, simulation, and artificial intelligence towards studying processes and systems in silico to better understand and discover in situ phenomena. So basically trying to bring the in silico world as close as possible to the real life world. In this paper, which is coming out very soon, in the next few days, hopefully, we similarly define 9 motifs of simulation intelligence, classes of complementary algorithms and methods to represent the foundation of what we're building here, the synergies in simulation and AI. And each of the SI motifs has momentum from the scientific computing and AI communities, but we present them in a way that really motivates their development in concert and in integrated ways to really overcome the shortcomings that are present across scientific domains with simulators and other computing technologies. And further, to really work towards our aim of expanding the scientific method with reliable and efficient hypothesis simulation analysis cycles. Our approaches in AI technologies can be better integrated such that we can more efficiently and perhaps produce newer methods from their combination. That is, rethinking up and down the stack, as reflected here, and across domains to avoid the trend that we see in scientific computing of narrow one-off solutions and siloed methods. At the core, or at the lowest level, is hardware. Basically addressing the question, can we flexibly leverage GPU, CPU, FPGA, and so on to run efficiently in many diverse scenarios, and especially in places that don't have the capabilities of supercomputing? And can we maybe use SI methods to design new accelerated hardware? For us, a lot of our development is one layer up at the operating system and application levels, which are red and purple here. How can we better enable the essential motifs like multi-scale modeling, physics-infused learning, causal discovery, by really rethinking these few sublayers of the stack? And we develop platforms that enable ecosystems to utilize the underlying technologies, from the smallest scales of particle physics and material science to socioeconomics and geopolitics, and then to the larger scales of climate science and astrophysics. And there are two main technologies, amongst others, that we focus on, particularly with the low level, the engine part that I was alluding to, called probabilistic programming and differentiable programming. Now, probabilistic programming is a relatively newer paradigm of AI, enabling generative models to easily be written and experimented with. Probabilistic programming essentially equates probabilistic generative models with executable software programs, which enables practitioners to leverage the power of programming languages to create rich and complex models, while relying on built-in inference backend that can basically take care of any model written in that specific probabilistic language. And the programs are generative models, so they relate unobservable causes to observable data to simulate how we believe data is really created in the world. Probabilistic programming, as you can tell, has a very close relationship to everything we're trying to achieve in simulation. Differentiable programming is another programming paradigm in which derivatives of a program are automatically computed and used in gradient-based optimization. And this is the backbone of deep learning. And for both of these topics, I'd like several more hours to introduce them both and dive in with examples. But in the context of this talk, I think it's really interesting to point out a theme of AI-driven expansions. Now, probabilistic programming expands the scope of probabilistic graphical models by allowing for inference and control over arbitrary models of programs, including programming constructs such as recursion and stochastic branching, things that we can't necessarily write in PGMs themselves. Analogously, differentiable programming is a generalization of neural networks in deep learning. If you think about the capabilities and the methods and the algorithms in the field of deep learning, differentiable programming is essentially an expansion of all of those, where we can think of arbitrary software modules with gradient-based optimization in differentiable programming. So together, these are things that make up the core of the simulation intelligence that we're developing, and they can really provide a much more expressive toolkit for knowledge representation. Now, I'd like to dive in, as I believe we have quite the mixed audience. There is a little bit of math ahead, but you don't necessarily need to grok everything to follow along. First, I would like to start by introducing this concept, which is a multi-year collaborative projects across nations and organizations and government and private sectors, Digital Twin Earth. And this has been motivated by the clear and apparent urgency for climate solutions, which motivates the need for modeling systems that are computationally efficient and reliable, lightweight for low resource use cases, informative towards policy and decision-making, and cyber-physical with varieties of sensors and data modalities. And I should say that we define a digital twin in the more precise sense of simulating the real physics and data generating processes of an environment or system, and with sufficient fidelity such that one can reliably run queries and experiments in silico. This is quite distinct from, for example, Internet of Things and cloud computing descriptions that use digital twinning as more marketing and labeling and branding. There are many machine learning and data related challenges for digital twin Earth, and these, of course, include simulations of multiple domains, geographies, and fidelities, not to mention the need to integrate real and synthetic data in a combined learning and inference framework, as well as multimodal data, so Earth observation, satellite imagery, along with streaming sensor data from hydrology systems. And I encourage you to find out more at the links that I list here, and definitely reach out if you're interested specifically in digital twin Earth and what we're doing with the NASA Frontier Development Lab. And the areas that we are building across the portfolio of digital twin Earth is in this physics-informed machine learning camp that integrates mathematical physics models with data-driven learning. And more specifically, making a machine learning method physics-informed amounts to introducing some appropriate observational, inductive, or learning biases that can steer or constrain the learning process to physically consistent solutions. And these three biases, they are observational biases, which are constraints based on the data sets. So what sort of images, for example, that you feed in. Inductive biases are built directly into the modeling architecture. And inductive biases, more common in neural networks and deep learning, would be convolutions for spatial representations over 2D and 3D images. And learning biases, which are quite often used in the physics-informed machine learning space, and is shown by this diagram here, where learning biases force the training of a machine learning system to converge on solutions that adhere to essentially the underlying physics of the problem. And to make this constraint or built it into the loss function, it's implemented by specific choices. Here you show that there's a physics-informed loss that is based on differential equations of the underlying system. And as you would expect, physics-informed machine learning is mostly applied with neural networks, which has produced a family of methods called physics-informed neural networks, or PINN, again, shown by this diagram. Now, these PINN approaches are currently limited to tasks that are characterized by relatively simple and well-defined physics, because you need to have a very cohesive and robust understanding of the physics in the environment in order to even think about building it into your learning architecture or loss functions or so on. If you can't build it in, particularly to physics-informed neural networks, you really struggle to try to resolve things that you're missing in the physics. And the characteristics of many of the physical systems that these things are, people would like to try to apply these to, particularly when you talk about multi-scale, complex, local and global climate systems, it's very difficult to implicitly encode those into a neural network architecture. And as I alluded, and as many of you probably know, problems in science and engineering, they involve solving partial differential equations, or PDE systems, which represent spatial and temporal dynamics. A promising direction in spatial temporal use cases is neural operator learning. And this is some work that was started by a group in collaboration with NVIDIA and Caltech, and then we've extended this in various ways, in particular scaling it to the complex climate scenarios that I had mentioned, and I'll show some of that later. In particular, this is working with FNOs, or Fourier neural operators, which use a Fourier layer that implements a Fourier transform, then a linear transform, and an inverse Fourier transform, which is essentially to mimic a convolution operation in a neural network. So just like I said, there's this inductive bias in convolutional neural networks for just standard natural images. If we have a Fourier transform, we can have the similar sort of inductive bias in a neural network where you have filters that are more aligned with spatial temporal dynamics instead of filters that are more aligned with the edges and curves that you would find in natural images. And you can see in the left figure on this slide, kind of comparison of what those filters might look like in the networks. And as always, the physics-informed machine learning tools, including the baseline FNO, really don't apply to real-world problems. The methods don't generalize well, and there are definitely model-specific failure modes. For example, many people might be aware of neural ODEs, which is a slightly different approach. But the trick in neural ODEs, that is doing forward and backwards calculations of derivatives at certain time points, we can find in a lot of real-world systems that that underlying assumption just doesn't hold. So it can break with the forward and backward pass of these approximate derivatives. But the real main problem is that real-world environments are far more complex than the simple data sets for publishing in conferences and journals, namely that they are multi-physics and multi-scale, and the boundary conditions really, really matter in these scenarios. And further, it's not uncommon to encounter hidden or unknown physics of interfaces and symmetry breaking or other singularities that you wouldn't really even foresee until you start working with these complex large-scale systems. And here, for example, is work that we've done with NVIDIA, NASA, and a few others in the context of digital twin Earth, where we were building a Fourier neural operator surrogate to accelerate coastal climate models. And in this case, this is a coastal climate model of Northern Europe that is the industry standard model, and we were able to simulate with the same precision and accuracy, but over 100 times the normal speed. And getting into an area that we even focus more on, something that I even personally am more excited about, is semi-mechanistic modeling. And in particular, what I'm showing here is graph-informed neural networks, which provide a computational advantage of some of the neural network or physics-informed neural network surrogates that I mentioned, while maintaining the advantages of structured modeling with probabilistic graphical models. Essentially, what happens here is a PGM encoding structured priors serves as input to a Bayesian network partial differential equation, which you can see on the lower route. And then there's neural network, and here's just a simple vanilla fully connected neural network that replaces certain nodes with surrogate neural networks for computational efficiency mostly. And what we really want to do is directly utilize the mechanistic modeling of the PGM, where we can encode the precise kind of representation of the environment and use that simultaneously with neural networks or even Gaussian processes, things that work as universal approximation to replace the computational bottlenecks, those nodes that either are super slow or we honestly don't even know much about. And the way that this is really, or in an interesting way, how this contrasts with the physics-informed neural network and some of the previous methods that I mentioned, is that here, this is more of a bidirectional relationship between the physics and the machine learning. In the previous case, you're taking some domain knowledge, some physics, some mechanistic equation, and you are using that or trying to inject an existing machine learning model or framework with it. In this case, what we're actually, we're able to do that, but also get back knowledge that improves our physics, improves our understanding of the environment in the first place. So we can actually use machine learning to inform the physics and actually inform the symbolic representations and the differential equations that define the overall system. And one way to do this kind of more concretely is with various methods for recovering missing physics. And this is one where I'm showing, it's called SINDI, Sparse Identification of Dynamical Systems. And this is something that's been around for a handful of years, but we're taking it in different directions to work with the semi-mechanistic models that I had shown earlier. And essentially what you do with SINDI is recover a symbolic representation of your dynamical system with the original method directly from data. You identify what the dynamical system should have been just by looking at the time series. And what this figure shows is a complex representation of how you build up a library of the different candidate constants and polynomials and trigonometric terms, and then you sparse identify which ones of those are relevant. Now, the practical limitations of this might seem obvious, they should. Namely, you need a ton of data, and also you can still rely or end up with a system that is essentially unidentified. It's really difficult to understand which environments can work with this and which ones cannot. As I mentioned, multi-physics and multi-scale scenarios, for the most part, wouldn't work with SINDI. However, when we bring in semi-mechanistic modeling, we can utilize the same sparse identification technique just with our graph-informed neural network, for example, to recover the symbolic representation and potentially the mechanistic equations that were previously learned from the data. So if we have a combination of data and differential equations going in to our semi-mechanistic modeling approach, and then we can have a combined physics-informed machine learning model that's output. We can use that model to, with sparse identification, to then go in the inverse direction and try to recover what would be the symbolic form, what would be the differential equations that are aligned with what we originally thought, or maybe were missing from the model in the first place. And that's what we mean by recovering missing physics. And speaking of those more complex domains where sparse identification really is not yet proven, this is digging into more specifically what I mean about multiphysics and multi-scale. A multiphysics environment is defined by coupled processes or systems with more than one simultaneously occurring physical fields or phenomena. And here are a couple examples which elucidate that, along with cascades of scales, which involve more than two scales of long-range spatial temporal interactions. And on the right is a diagram of this with various physics and scales to simulate turbulent flow within a nuclear reactor core. And on the left is a completely different application. It's mechanisms in blood-brain barrier flow with various methods listed for spatial temporal scales. And getting back to climate, this is an example of what we've done in Digital Twin Earth with, in particular with USGS, looking at a very complex multi-physics, multi-scale coastal climate simulation. This is here, the San Francisco Bay Area, where we're looking at multiple physics and multiple scales and atmospheric models and tide models just in that complex mesh on offshore that you see there. And then inshore, completely different environments and physics that represent the hydrology and water and the flooding maps, and then also how those interact with different parts of the coastline. And this is something, I do have it, that we have been developing, like I said, with USGS for accelerated real-time decision-making, but really a better understanding of how these systems work, and also in a 3D way. I think I'm running short on time, so I'll get right to the meat of it, is the Nobel-Turing challenge. I think climate exemplifies this statement in obvious and pressing ways, that we cannot really solve our problems with the same level of thinking that created them. And if we think back to the intro of this presentation on the science of science, I posed this suggestion that progress is bottlenecked because of limitations representing real-world processes in simulations. But more abstractly, I'd like to suggest that scientific progress is constrained by the spaces of hypotheses and solutions for which we as humans really have purview. How do human priors and biases restrict our exploration of these spaces? If there is one thing that we can state with really utmost confidence about these spaces of science and knowledge, it's that there are far more unexplored space than we can possibly imagine. That I think has to be fundamentally true about the state of the world. And here in this diagram, I'm showing kind of a simple, of course not to scale, conceptualization of the DeepMind's approach to expanding the space from human-played games in Go to those that were the entire possibility of what's within the human purview, like I mentioned, to things that were completely new, generated by the artificial intelligence system. And what we're trying to do with simulation intelligence is take that similar vision to physical sciences. Which brings us to this Nobel-Turing challenge, essentially developing and validating AI systems capable of Nobel-caliber scientific discoveries and in highly autonomous ways. There's a lot of people working on this. I list a handful of us here that have been really trying to take lead and organize across domains, institutions, and nations even. And we're starting to plan and formalize this more with more papers and materials and hopefully workshops and meetings coming out in the next year or so. And I definitely want to note that winning the Nobel Prize is used really as a symbolic target illustrating the level of discoveries the challenge is aiming at. The value really lies in the development of machines that can make discoveries continuously and autonomously, rather than winning any award, including the Nobel Prize. It's really used as symbolism to trigger, well, both inspiration and controversy. That's entirely intentional. Now, as I've discussed, scientific discovery really presents us with many different challenges compared to games such as chess and Go and other domains like autonomous vehicles. Scientific discoveries require an order of magnitude larger hypothesis space, a more elaborate verification process, and the integration of scientific devices and modules in humans. The Nobel-Turing challenge concept aims to encapsulate these challenges and definitely more, including things like societal implications of AI-driven discovery. And we also very much want to motivate multiple paths forward. The explicit goal of the challenge is to develop an AI system that has highly autonomous capabilities to perform research. While human scientists already use a wide range of AI tools for many tasks that contributed to discoveries, these really cannot be considered AI scientists, right? Because they only address narrow aspects of the scientific process. They lack autonomy in setting their goals, in hypotheses, and interpreting results, and going back to the drawing board, so to speak, let alone communicating findings and collaborating with others. The AI field in general is very much focused on modeling and design, whereas highly autonomous science calls for much more, not to mention the immense data and systems engineering around all of these parts of workflows. Even so, mainstream AI technologies, if you kind of just slide them into, for example, this workflow, they can really suffer in this paradigm, which I show here in red. There are many issues with things like data curation and labeling, the inability to quantify and propagate uncertainties, partially due to modeling, partially due to the data issues, and downstream limited interpretability by human experts and other downstream users. And then at the top there is something that in particular, my company in our applications, we focus on as a key value prop, is this sim to real and attrition in a few different ways. Where the design of potential solutions, whether it's molecules or climate mechanisms for energy storage, what have you, the gap from design to synthesis to validation and deployment, those gaps are insurmountable in many, many ways. And if we can use simulation intelligence to narrow those gaps, then we can really accelerate that part of the workflow. And here, like I was saying, we address a lot of these issues in important ways. And here's a list of them, just some of them in the green and the purple in this figure. For instance, the semi-mechanistic modeling and physics-infused learning I shared earlier is essentially the modeling understanding phase. And it's also critical that the sim-to-real transfer phase. And we further suggest that these have to be integrated, not just step to step, but integrated altogether in closed loop ways that coordinates learning and information sharing between upstream and downstream phases. Two of the simulation intelligence motifs we're focusing on really help with this human-machine teaming workflow and potentially close the loop with hypothesis generation. That's specifically simulation-based inference, which I hope many of you are familiar with, and causal discovery. And again, you can look out for our paper and dig in there for many, many more details and examples on those. And with regards to working on the Nobel-Turing challenge, there are, or rather just working on similar aligned goals and visions, there are plenty of groups working on this. It's not just us. I don't want to leave with that impression. And many others doing very important, impressive work, particularly in the area of chemistry and material science, with different variations of the data-driven modeling and synthesis processes that I'm showing here. Here are a couple examples from recent publications. Now, how does this relate to Nobel-Turing challenge, and what is to become of the challenge? Where does simulation intelligence fit in? How do people get involved? These are still open questions, to be honest. And some of these open questions are existing questions that we're trying to tackle are, will there be a grand challenge like that which kicked off the autonomous driving field in 2003? Or something more like an X Prize with checkpoints and challenges that are agnostic to the implemented methods. So like I was saying, you can motivate multiple paths going forward towards these collective goals. These are all to be determined, and I would put my money on all of the above in various ways, particularly because this Nobel-Turing challenge is not going to take over the course of years, but it's on the order of decades. There are most people that think 2050, some people are saying 2030, but nonetheless, it is going to be something that is a long-term effort and an interdisciplinary one at that. And I'll also mention that our approach with my company is distinct in many of the ways that I shared today, but also kind of holistically. We're not necessarily going all in end-to-end on one specific use case or vertical, really. Rather, we're more interested in building tools and platforms that enable others to do that in a horizontal way. That is, we're building the operating system for simulation intelligence. Laboratory processes and equipment and methods and practices, even for our publications and everything, are currently designed for the traditional deductive scientific method, where tools assist human scientists and technicians. Simulation intelligence, however, provides the opportunity to rethink this human-machine relationship towards new scientific methods that are inductive, data-driven, more efficient, and explore new territories, and in general, managed by AI in a way that isn't centered on automation, managed by AI to really accelerate our scientific discoveries overall. Now, definitely keep an eye out for that paper that I mentioned a few times and other materials and announcements in the coming weeks and also the coming months. We have a lot more about the Focus Research Organization, our partnerships, publications, and projects. And please reach out if you're interested in learning more, asking questions, chatting. Find us on LinkedIn, Twitter, and you can also just reach out directly about careers, partnerships, and anything. Thank you.
Okay, hi, Alexander. Thank you for the talk. That was really informative. We'll just go straight to the Q&A. We have some questions here from Ricardo. He's asking, how do you enforce symmetries of the problem in neural network and how it generalizes to arbitrary symmetries?
Yeah, that's a great question, Ricardo. If I were to give a slightly more in-depth presentation on the physics-informed machine learning, I would have been sure to talk about equivariant neural networks and taking this concept of equivariance to even other architectures or methods in machine learning, where equivariance essentially tries to exploit these symmetries. It's another way of enforcing some of those constraints as an inductive bias directly in the architecture, like I was saying.
Okay, thank you. He also has another question. Are you considering quantum machine learning for some parts of the climate model of our digital twin edge project?
To be honest, that hasn't necessarily come up much in the realm of digital twin Earth. Digital twin Earth is still making heavy use of a lot of the physics-informed machine learning, and existing even data engineering problems are really significant hurdles in digital twin Earth. Whereas quantum computing, quantum machine learning even, are things that are, to our knowledge, quite unproven and could be integrated down the road, but we haven't really crossed that bridge yet.
Okay. Thanks so much for that. And that's you have an interesting question from Matthew Darling. I said that the original neural ODE paper was famously ripped apart by one of the authors. I haven't kept up with the research since, so I'm wondering if the method has become more robust and well-defined since then.
Yeah, thanks. I'm glad you picked up on that. So David Duvenod, who's the lead author, or not the lead, but it's from his lab. I believe it was the next year at NeurIPS where he gave that talk ripping apart his own work about a lot of the assumptions they were making. And I did mention one way where neural ODEs fail. I don't know if David mentioned it in his talk a couple years ago, or if that's come about more recently, but that's one of a handful of ways where neural ODEs, they do essentially fall apart. And to your question about the progress since, yes, they've definitely been improved, but at least my suggestion and the way that we are viewing the problems with which you would apply neural ODEs, we're taking different approaches. In particular, universal differential equations, which is something you can look up. It's mostly out of Chris Rakalkis' lab at MIT, which is a more robust semi-mechanistic approach that eliminates most of the problems of neural ODE because it isn't trying to really do away with differential equations and just learn them away, but it is utilizing differential equations to improve the learning of other parts of the system.
Okay, thanks so much. And we have a question here from Jane Dodd. It seems like AI might be particularly well suited to doing science in modes that humans struggle with, such as meta studies or integrating research across disciplines. Is there current work in these directions? So
that's interesting. If you have specific ideas about integrating different modes and fields in an automated machine learned way, that would be very interesting to hear. I know, because I would actually push back and say it's quite the opposite. I think AI, at least in the current state, is very well suited for domain-specific, narrow, isolated, and when we talk about science, well-posed problems, things that are very well constrained. And when you try to cross boundaries, across other disciplines, that's when you're trying to go outside the box, so to speak, across those boundaries, and you aren't able to really make connections in a useful, let alone causal way. I do know that there are some works in the area of biomedicine where there's a company, it might be Causality, something with causal in the name, that does knowledge graphs on biomedical literature. And it does that better than anything I've seen as far as trying to establish the really significant correlations in the graph, but also causal connections across the literature. Otherwise, I don't think people have yet really taken artificial intelligence to try to say or answer a question of how do we take these methods from synthetic biology in agriculture and apply them to maybe generating new molecules or materials for a different domain. I don't think we're quite there.
Oh, okay, thanks for that answer. I will still have a minute on our time. If you want to reach out to Alex, the email and the LinkedIn are on the page now. You can also put it in the chat if you want to, Alex, so that people can reach out to you for more questions. And in the meantime, if you missed any talk, you can check the replay button and get the talk that you missed. And we also encourage you to visit our booth for awesome giveaways from our wonderful sponsors. So thank you so much, Alex, for the talk, and thank you for coming here for this section today. Okay.
Yeah, thank you. Thank you, everyone.
Okay, so have a wonderful day.